That solid ground beneath your feet is a lie. It is the ultimate product of a planetary engine operating deep within the Earth. The continents we call home were not always here. They were engineered over billions of years by the immense heat and churning motion of our planet's core. By the end of this story, you will see every mountain, every coastline, and every plain as a direct message from a world of unimaginable power far below the surface. How did a ball of searing hot metal at the center of our planet manage to build the very land we live on? And why does this process make Earth uniquely suited for life in a hostile solar system? What does it mean to live on a planet that is actively building itself beneath us? Think of our planet as a colossal factory, but one that operates on a timescale almost impossible for us to comprehend. This factory's engine room is its layered interior, a place of unimaginable pressure and heat. At the very center sits the inner core, a solid ball of iron and nickel, squeezed into a crystalline state by the weight of the entire world pressing down on it. Wrapped around this solid heart is the outer core, a churning ocean of liquid metal. This relentless motion is the source of Earth's protective magnetic field, a vital shield against the sun's dangerous radiation. Above this metallic core lies the mantle, a 2,900-kilometer thick layer of hot, solid rock. But solid is a misleading term here. Under the immense heat and pressure, this rock does not shatter. Instead, it flows, creeping along in currents so slow they make glaciers seem swift. This vast, syrupy realm is the workshop where the raw materials for continents are forged. And finally, riding on top of this restless foundation is the thin, brittle shell we call home, the crust. It is broken into enormous puzzle pieces, the tectonic plates. This entire structure is powered by a primal fire, the leftover heat from Earth's violent formation, and the continuous decay of radioactive elements deep within the rock. That heat has to go somewhere, and its escape drives the entire machine, creating the convection currents that slowly, relentlessly, move the plates and shape the world above. So what keeps this planetary engine running after 4.5 billion years? The answer lies in a deep and relentless fire. This is not the simple, cooling ember of the planet's birth, but a sustained nuclear reaction. The primary fuel for our world comes from two powerful sources. The first is primordial heat, the vast reservoir of energy left over from Earth's violent assembly. This is the fading warmth from the colossal collisions that built our planet, a buried treasure of thermal energy. But more important today is the second source, the continuous furnace of radioactive decay. Deep within the mantle and core, unstable atoms are constantly breaking down. Isotopes like uranium-238, thorium-232, and potassium-40 are scattered through the rock, and as their nuclei split apart, they release a steady, immense pulse of heat. This is a form of natural nuclear fission, a built-in reactor that has been burning for billions of years. This energy is not spread out evenly. It creates vast, rising plumes of superheated rock and powers the slow, churning currents within the mantle. That churn is the primary conveyor belt that drags the tectonic plates across the globe. Without this internal atomic furnace, Earth's core would have cooled long ago. The magnetic field would have faded, the mantle would have solidified, and the great geological machine that builds continents would have ground to a permanent halt, leaving our world a static, frozen sphere. This great churn in the mantle is the planet's primary circulatory system. Think of a pot of thick soup heating on a stove. The soup at the bottom of the pot, closest to the heat source, warms up, expands, and becomes lighter, causing it to rise in a slow, rolling motion. As that soup reaches the cooler surface, it loses its heat, becomes denser, and begins to sink back down, only to be reheated and rise once more. This cycle is convection, and it is the exact same principle that governs the motion of rock within Earth's mantle, though the timescale is almost unimaginably longer. Over millions of years, rock behaves like a thick, stubborn fluid. Superheated rock from the deep mantle, energized by the core's atomic furnace, becomes buoyant and begins an achingly slow ascent. It can take hundreds of thousands of years for a single plume of this material to travel just a few dozen kilometers. As this rock nears the cold, rigid crust, it begins to cool down. It contracts, becomes denser, and its journey reverses, starting the long, slow sink back into the depths. This creates a planetary conveyor belt, a continuous cycle of rising and falling material that spans the entire globe. These colossal convection currents are the invisible hands that grip the tectonic plates from below. They provide the push and the pull that drags these vast slabs of crust across the face of the planet. Where two of these currents diverge, pulling material away from a central point, they tear the crust apart, creating gaping wounds in the ocean floor. Where currents converge, forcing material together, they slam continents into one another with irresistible force. Every great geological event that shapes our world, from the birth of a mountain range to the opening of a new ocean, is orchestrated by this deep, rhythmic pulse. The continents themselves are the most dramatic products of this relentless, heat-driven dance. These ancient foundations are the closest thing our planet has to permanent real estate. Known as Cratons, these are the indestructible seeds of the continents. You can think of them as the original, unshakable bedrock, the anchors upon which everything else was built. Some of these formations are over 4 billion years old, making them nearly as old as the Earth itself. To stand on one is to stand on the very first land that ever solidified from the planet's primordial chaos. But how did these first islands of stability emerge from a globe covered in a roiling ocean of magma? The process began when the Earth was a far more violent and extreme place. The mantle was significantly hotter then, churning with an intensity we can scarcely comprehend. This widespread heat caused massive melting, leading to the eruption of colossal amounts of dense, dark basaltic lava across the young planet's surface. This formed the first primitive crust, a thin, unstable skin that was constantly being recycled back into the inferno below. The true magic, the birth of the continents, happened through a crucial refining process called partial melting. Imagine taking that dark, heavy basalt and reheating it. You do not melt the entire rock into a uniform liquid. Instead, the specific minerals with the lowest melting points turn to liquid first. These are the lighter elements, the ones that form minerals like quartz and feldspar. This molten material, now less dense than the surrounding rock, behaved like bubbles in a boiling pot. It began to rise, squeezing its way upward through fractures and weaknesses in the solid basalt. As this buoyant magma cooled and crystallized, it formed a completely new kind of rock, a light-colored rock we know as granite. This was the fundamental building block of the continents. Unlike the dense basalt of the ocean floor, these granite blobs were too light, too buoyant, to be dragged back down into the mantle by the churning convection currents. They were essentially unsinkable. For the first time in Earth's history, material had escaped the relentless cycle of destruction and rebirth. These unsinkable granite rafts began to accumulate, colliding and welding together over hundreds of millions of years. Each collision added more material, slowly, painstakingly building up the first permanent continental nuclei. these original cratons became the unshakable anchors, the testimony to the core's initial, successful efforts at forging something lasting from the fire. These ancient cratons provided the foundation, but continents do not remain static. They grow. This expansion happens at their volatile edges, in places that function as the planet's ultimate recycling plants, known as subduction zones. Imagine the slow-motion collision of two immense tectonic plates. On one side, the dense, heavy basalt of an oceanic plate. On the other, the buoyant, unyielding granite of a continental plate. When they meet, there is no compromise. The heavier oceanic plate is forced to give way, bending downward and plunging back into the hot mantle from which it came. This is the process of subduction, and it is the primary engine of continental construction. But this is not a simple act of destruction. It is a transformation. As the oceanic plate descends, it does not travel alone. It carries a precious cargo of seawater, locked within its minerals, and a blanket of ocean sediments, the accumulated dust of millions of years. This watery mixture is the secret ingredient. When it reaches the intense heat of the upper mantle, the water is squeezed out, percolating upward into the solid rock above the descending slab. Water acts as a powerful flux, drastically lowering the melting point of that mantle rock. Just as salt lowers the melting point of ice on a winter road, this water forces the overlying mantle to melt, even at temperatures that would normally keep it solid. This newly formed magma is fundamentally different from the material that descended. It is infused with silica and other light elements scavenged from the melted sediments. This makes it less dense, more buoyant. It begins to rise, forcing its way upward through the thick continental crust like a hot air balloon through a dense atmosphere. This journey has two dramatic outcomes. Sometimes the magma erupts with explosive force, creating the iconic cone-shaped volcanoes that line the Pacific Rim. These volcanic chains are the visible evidence of a subduction zone at work. At other times, the magma gets trapped, cooling slowly for thousands of years deep within the crust. There, it crystallizes into vast subterranean formations of granite called batholiths. These are the hidden skeletons of mountains, the new bedrock that is permanently welded onto the edge of the continent. Every eruption, every hidden granite formation, is a delivery of new land. The continent literally grows piece by piece, built from the recycled remains of the old ocean floor. That line of fiery mountains is the planet's most dramatic construction zone. These are volcanic arcs, the direct and spectacular result of an oceanic plate plunging into the mantle. Each volcano in the chain acts like a chimney, venting material that was, until recently, part of the Earth's deep interior. The magma that feeds them is special. It is not the fluid, runny lava that oozes from Hawaiian volcanoes. This magma is andesitic to granitic, which means it is loaded with silica, making it thick, sticky, and full of trapped gases. When this viscous magma finally reaches the surface, it does not flow gently, it explodes. These are some of the most violent eruptions on Earth, blasting colossal amounts of lava, ash, and rock fragments high into the air. That debris does not disappear. It falls back to Earth, piling up layer upon thick layer around the volcanic vent. Over thousands of eruptions spanning millions of years, this accumulated rubble builds not just a single volcano, but an entire mountain range. The Andes in South America are a perfect living example. This colossal wall of rock running the entire length of the continent is being built today by the ongoing subduction of the Pacific Ocean floor beneath it. Every rumble, every eruption is another delivery of new land. The rock formed here has a crucial property. It is less dense and more buoyant than the heavy basalt of the ocean floor it borders. This ensures it can never be dragged down into a subduction zone. it is permanently added to the continental shelf, a brand new piece of real estate forged directly from the mantle's fiery workshop. But the fiery volcanoes are not the only way continents expand. There is another, more dramatic method of construction, one that involves the assembly of entire geological provinces transported from across the globe. Continents are not the monolithic blocks they appear to be on a map. They are complex mosaics stitched together from a wild variety of geological fragments called terranes. The process that welds these foreign bodies onto a continent is known as accretion. Picture a massive oceanic plate, a conveyor belt of ancient seafloor sliding inexorably toward a waiting continent. Riding on this plate are exotic passengers, island chains, submerged volcanic plateaus, or even small continental fragments. These are the terranes. When the plate reaches the subduction zone and begins its descent, these passengers face a choice. They are too buoyant, too thick to follow the dense ocean floor down into the mantle. Instead of subducting, they collide with the continent and are scraped off, permanently sutured to its edge. This is not a gentle docking. It is a colossal, slow-motion collision that crumples rock, uplifts new mountain ranges, and literally widens the continent. The western margin of North America is a textbook example of this chaotic assembly. From Alaska down through California, the continent is a colossal geological jigsaw puzzle, assembled from hundreds of these accreted terranes over hundreds of millions of years. Each piece has its own unique history, its own fossil record, and its own rock composition, completely different from its neighbors. They were once scattered across an ancient ocean, carried on tectonic currents, and finally slammed into the continent by the relentless push from the core's engine below. This process shows that continental growth is not always a slow, internal cookery. Sometimes the planet's deep engine acts as a global transport system, picking up pre-formed crustal fragments and delivering them to the continental shores, stitching the world together one colossal piece at a time. This grand assembly and dispersal of land is part of a planetary heartbeat, a rhythm that pulses over hundreds of millions of years. The continents we see today are just a single frame in a slow-motion film of Earth's history, a film directed by the heat rising from the core. This is the Supercontinent Cycle, the ultimate expression of our planet's deep thermal engine at work. The most famous of these giant landmasses was Pangaea, a colossal continent that brought nearly all of Earth's dry land together 250 million years ago. But Pangaea was not the first, and it will not be the last. This cycle of coming together and breaking apart has repeated itself over and over again throughout our planet's deep history. The force that drives this epic dance is the long-term pattern of convection within the mantle. Think of those slow, churning currents as the hands of a clock, moving the continents on a timescale we can barely grasp. For a time, these currents pull the scattered continents together, forcing a slow-motion collision that builds a single, world-spanning supercontinent. Yet this very act of creation contains the seeds of its own destruction. A supercontinent acts like a giant blanket, smothering a vast portion of the planet's surface. It insulates the mantle beneath it, trapping the immense heat trying to escape from below. This heat has nowhere to go, so it begins to build up, causing the entire continental landmass to slowly dome upward and weaken from within. The supercontinent, stressed and heated from below, eventually ruptures. Giant fissures tear across its surface, becoming new rifts where fresh magma rises to form new ocean basins. The continent splits, and the fragments begin their long journey apart, carried away by the very mantle currents that once brought them together. This cycle is the core's way of regulating the planet's temperature and geography. It dictates everything from global climate and sea levels to the very course of evolution itself. When continents are united, climates become extreme with vast, arid deserts in the interior. When they break apart, new coastlines form, creating shallow seas that teem with life and altering the global climate. The rise and fall of species, the opening and closing of oceans, all are tied to this billion-year pulse from the planet's heart. The world we walk on is not a permanent stage, but a temporary arrangement in an endless, heat-driven dance. This endless pulse of creation and destruction follows a predictable rhythm, a pattern we now call the Wilson cycle. It is the story of an ocean's life, from its fiery birth to its final, crushing death, a tale written by the deep currents of the mantle. The cycle begins with a continent under stress. Trapped heat from below causes the land to bulge upward and stretch thin, until a deep, linear wound, a continental rift, tears across its surface. The East African Rift Valley is a living snapshot of this very process in its earliest stages, a place where a continent is actively being pulled apart. As the rift deepens, the crust thins to a breaking point, and the land sinks below sea level. Seawater floods in, and volcanic activity intensifies along the central valley, spewing forth new basalt. This is the moment a new ocean is born. The young basin is narrow and confined, a place like the modern Red Sea, where the Arabian Peninsula has already torn away from Africa. Its shores still mirror images of each other. As the mantle's convection currents continue to pull the continental fragments apart, the process of seafloor spreading kicks into high gear. Fresh magma wells up along the mid-ocean ridge, the underwater mountain chain that runs down the center of the new basin. This new crust is hot and buoyant, causing the ocean floor to ride high. The basin widens dramatically, evolving into a mature ocean like the Atlantic. Its coastlines are now separated by thousands of kilometers of open water, and the continents on either side carry completely different ecosystems, their biological histories forever divided by the growing expanse of blue. But this maturity contains the seeds of the ocean's own demise. As the oceanic crust travels away from the hot mid-ocean ridge, it slowly cools. It contracts, becomes denser, and begins to sink lower into the underlying mantle. Over tens of millions of years, this dense, old crust becomes a liability. Eventually, its own weight becomes too much to bear. At one of its margins, it finally gives way, bending downward and initiating a new subduction zone. Once subduction begins, the ocean's fate is sealed. The basin stops expanding and starts to shrink, closing in on itself like a colossal drawstring bag. The ocean floor is now being consumed faster than it is being created at the distant mid-ocean ridge. The final act of the Wilson cycle is a slow-motion, continent-shattering collision. As the ocean basin narrows to a mere remnant, the two continental landmasses on either side, which were once joined as one, are now on a direct collision course. They are both too buoyant to subduct. There is nowhere for them to go but into each other. The result is one of the most powerful forces on the planet, a continental collision that crumples the leading edges of both landmasses, folding and thrusting rock upward to form a new mountain range. The Himalayas stand as the ultimate monument to this process, a towering chain built from the wreckage of the ancient Tethys Ocean, which closed when India slammed into Asia. This collision marks the end of the ocean's life and the creation of a new supercontinent, welding the land back together. And beneath it all, the mantle's heat begins to pool once more, ensuring that this new supercontinent will, in time, also be torn asunder, starting the entire magnificent cycle all over again. The planet's great tectonic conveyor belt does not have a monopoly on fire. Deep beneath the plates, another kind of geological phenomenon is at work, one that rises from the very frontier of the core itself. These are mantle plumes, the deep Earth's blowtorches. While most volcanoes form at the edges of plates where they collide or pull apart, mantle plumes burn through the plate's center, creating isolated hotspots of intense volcanic activity. A mantle plume is not a broad, slow current like those in the upper mantle. It is a narrow, focused column of rock that is hundreds of degrees hotter than its surroundings. This superheated material begins its journey at incredible depths, possibly from the very boundary where the metallic core meets the rocky mantle. Driven by its intense buoyancy, it punches upward through 2,900 kilometers of solid rock, a journey that can take tens of millions of years. When this focused jet of heat finally reaches the base of the rigid lithosphere, it does not stop. It presses against the cold crust like a blowtorch against steel, melting everything above it and creating a portal for magma to reach the surface. The effects are spectacularly different depending on whether this plume rises under a continent or an ocean. Beneath a continent, the results are apocalyptic in scale. The plume domes the land upward, creating a vast, high plateau. It triggers colossal volcanic eruptions that do not build elegant cones, but instead flood the landscape with rivers of lava. These are flood basalt events, where millions of cubic kilometers of molten rock pour out in a geologically short time, covering entire regions in layers of black basalt thousands of feet thick. The Deccan Traps in India are the scar of such an event, a volcanic outpouring so immense it is linked to the mass extinction that wiped out the dinosaurs. This thermal assault also weakens the continent from within, stretching it thin and often providing the final, fiery push that rips a supercontinent apart. When a plume rises under the thin skin of the ocean floor, it creates something more familiar but equally revealing. It builds a volcano on the seabed that can grow tall enough to break the surface, forming a volcanic island. But the story does not end there. The tectonic plate above is constantly in motion, drifting slowly over the stationary, fixed hotspot. As the plate moves, the volcano is carried away from its magma source, becoming extinct. The plume, however, continues to burn, and it immediately begins building a new volcano in the old one's place. Over millions of years, this process paints a dotted line of volcanoes across the seafloor, a chronological chain that records the absolute direction and speed of the plate's journey. The Hawaiian Islands are the most famous example of this phenomenon. The big island of Hawaii is currently sitting over the hotspot, volcanically active and still growing. To its northwest, a string of older, extinct islands and submerged seamounts stretches for thousands of miles, each one a former version of Hawaii, now dormant and being eroded back into the sea. This chain is a timeline frozen in rock, a direct recording of the Pacific Plate's motion over a fixed fire rising from the planet's deepest engine. These plumes are more than just geological curiosities. They are direct messengers from a realm we can never visit, proving that the core's influence is not just a slow, pervasive churn, but can also be a focused, violent, and world-altering force. This planetary engine provides a defense that reaches far beyond the ground beneath our feet. The churning ocean of liquid iron in the outer core acts as a colossal electrical generator, a self-sustaining system known as the geodynamo. As this molten metal swirls and rises, it spins vast, slow currents that generate powerful electrical currents. These currents, in turn, create our planet's magnetic field, an invisible shield that extends tens of thousands of kilometers into space. This magnetic bubble is our first and most important line of defense against the sun. Our star constantly bombards us with the solar wind, a supersonic torrent of charged particles. Without the magnetic field, this relentless stream would strike our atmosphere directly, gradually but surely stripping it away, molecule by molecule, just as it did to the planet Mars. But the geodynamo deflects this onslaught, bending the solar wind around our world and safeguarding the air we breathe. This protection is fundamental to everything on the surface. A stable atmosphere allows for the gentle, persistent weathering of rock by wind and rain. This breakdown of rock is the first step in creating soil, the fertile foundation for terrestrial life. It also drives the long-term carbon cycle, where carbon dioxide is pulled from the air, locking it away in carbonate rocks on the seafloor for millions of years. This process acts as the planet's thermostat, preventing a runaway greenhouse effect and maintaining the stable, temperate climate that complex life requires. Without the magnetic field generated by the core's relentless churn, Earth would be a barren, airless rock scoured by solar radiation. There would be no soil, no water cycle as we know it, and no stable climate. The slow, patient geological processes that built the continents and allowed life to gain a foothold would have been impossible. The engine in Earth's heart does not just build the ground we walk on. It actively maintains the very conditions that make that ground a home. This grand separation of elements was the planet's first and most important act of self-organization. When Earth was young, it was a churning sphere of molten rock, a global magma ocean heated by the relentless bombardment of asteroids and the decay of radioactive elements. In that seething chaos, gravity began to do its meticulous work. Dense, heavy elements, primarily iron and nickel, were pulled relentlessly downward, sinking through the liquid rock like stones through water. This great descent created the planet's metallic core, a reservoir of immense density that anchors our entire world. At the same time, lighter elements and compounds were displaced, floating upward like the froth on a pot of boiling soup. These were the silicates, minerals rich in silicon and oxygen. This process, known as planetary differentiation, gave Earth its fundamental layered structure, the core, the mantle, and eventually the crust. But the sorting did not stop there. The mantle itself was not a uniform mixture. Within its silicate composition, certain elements were geochemically fussy. They did not fit neatly into the crystal structures of the dominant mantle minerals. These are the incompatible elements, atoms like silicon, aluminum, potassium, and uranium that were constantly being excluded as the mantle rock slowly solidified. These rejected elements became the building blocks of the continents. Through the persistent process of partial melting, they were systematically extracted from the mantle, concentrated into buoyant magmas, and delivered to the surface. The continents are therefore more than just land. They are the planet's geochemical reservoirs, the ultimate expression of a 4.5 billion year long refining process. The core, by drawing the heaviest metals into its center, set this entire chain of events in motion. It created the chemical imbalance that allowed the lighter, more diverse materials to rise and form the unique, complex crust we call home. Without that initial gravitational sorting, our world would be a geologically bland sphere, lacking the dynamic interplay between core, mantle, and crust that makes Earth so uniquely alive. This persistent buoyancy is the continent's ultimate defense against time. Even as wind and rain relentlessly scour a mountain range down to its roots, the land itself refuses to disappear. This remarkable phenomenon is governed by a principle known as isostasy, the gravitational balance that allows the crust to float on the denser, fluid-like mantle beneath it. Picture a simple block of wood floating in a tub of water. A thick, lightweight block will ride high with much of its mass elevated above the surface. A thin, dense block will sit much lower, barely breaking the waterline. This is the fundamental relationship between continental and oceanic crust. The continents are the thick, buoyant blocks of granite, while the ocean floors are the thin, dense slabs of basalt. They are both floating on the same underlying medium, the malleable mantle. and they each settle at a height dictated by their own thickness and density. This is why the continents form the high ground and the ocean floors form the deep basins, a global equilibrium established by the very nature of the rocks themselves. But isostasy is not a static state. It is a dynamic, responsive system. When a mountain is worn down by erosion, a colossal weight of rock is removed. The crustal block, now lighter, experiences a buoyant upward push from the mantle. It rises slowly in a process called isostatic rebound, bringing the deep, uneroded roots of the mountain closer to the surface. The mountain, in effect, floats upward as its top is shaved away. The opposite effect occurs when a great weight is added. During an ice age, colossal glaciers thousands of feet thick press down upon a continent, forcing the crust to sink deeper into the mantle. When those glaciers finally melt and retreat, that immense weight is lifted. The land, freed from its burden, begins a slow, deliberate ascent back to its original level. We can see this happening today in places like Scandinavia and Canada, where the land is still rising century after century, recovering from the last ice age. This constant, invisible adjustment is what makes the continents virtually indestructible. They are not fixed in place. They are resilient, floating rafts, eternally bobbing on the slow currents of the mantle. The erosion that wears them down is counteracted by the buoyancy that lifts them up. This grand, self-correcting balance ensures that the continental crust, forged in the planet's fiery youth, remains a permanent feature of our world, a direct and elegant consequence of the density differences set in motion when the core first separated from the mantle billions of years ago. Water's role in this planetary construction project is far more than just filling the oceans. It is the essential chemical agent, the catalyst without which the continents as we know them could not exist. This begins where the ocean floor itself vanishes, dragged down into a subduction zone. The descending slab of crust is not dry. For millions of years, it has been hydrating, its volcanic rocks reacting with seawater to form new, water-rich minerals. As this heavy, wet slab sinks into the hot mantle, it is slowly squeezed and cooked. The intense pressure and heat force the water out like wringing a sponge. But this water does not simply vanish. It percolates upward, infiltrating the solid mantle rock that lies directly above the descending plate. Here, water performs its most crucial trick. It drastically weakens the atomic bonds within the mantle rock, lowering its melting point by hundreds of degrees. This is the same principle that makes salt melt ice on a road. Solid rock that would normally remain frozen at that depth and temperature is now compelled to melt. This newly formed magma is not like its parent rock. It is infused with silica and other light elements, transforming it into a buoyant granitic brew. This is the primary source of the magma that builds continental crust. Without that constant injection of water from the subduction slab, the mantle above would remain largely solid, and the volcanic arcs that line the continents would fall silent. The entire process of building new land would slow to a geological crawl, yet water's work continues long after the mountains are built. On the surface, rain and ice relentlessly attack the high peaks, breaking solid granite into sand and clay. Rivers then act as the planet's conveyor belts, carrying this eroded debris down to the sea where it settles in thick layers on the continental shelves and the ocean floor. This is not a one-way trip into the deep. When that future ocean floor is itself pulled into a subduction zone, these sediments, now packed with the mineral wealth of the continent, are scraped off and added to the growing landmass or melted down to fuel the next generation of continental growth. Water is the great recycler, the lubricant that keeps the entire machine running smoothly. It is the indispensable partner to the core's heat, a chemical collaborator in the billion-year-long project of building a world fit for life. This slow, patient weathering of rock is the key to a planetary thermostat. The Carbon-Silicate Cycle is a feedback loop of breathtaking elegance, one that has maintained Earth's climate within a habitable range for billions of years. It begins with a simple chemical reaction in the sky. Carbon dioxide in the atmosphere dissolves into raindrops, creating a weak carbonic acid. This is the same mild acid found in soda water, but over geological time, its effect is profound. When this acidic rain falls on the continents, it slowly eats away at silicate rocks, the very granite that forms the bulk of the land. This chemical weathering breaks the rocks down, releasing calcium and magnesium ions, which are then washed into the rivers and carried to the sea. In the warm, shallow ocean waters, microscopic organisms and chemical processes use these ions to build their shells and skeletons from calcium carbonate. When these creatures die, their remains sink to the seafloor, accumulating layer upon layer to form vast deposits of limestone and other carbonate rocks. This is how carbon, once a gas in the air, becomes locked away in solid stone on the ocean floor. But the cycle does not end there. The relentless engine of plate tectonics takes over. That seafloor, with its immense cargo of limestone, is eventually dragged into a subduction zone. The carbonate rocks descend into the mantle, where they are subjected to immense heat and pressure. This cooking process breaks the carbonate minerals down, releasing the carbon dioxide gas once more. The gas then follows the path of the magma it helped create, rising through the crust and being vented back into the atmosphere through volcanic eruptions. This completes a loop that can take millions of years. The true genius of this cycle is its self-correcting nature. It functions as a global thermostat. If the planet grows too warm from a surge in volcanic activity or some other event, the increased heat accelerates evaporation and rainfall. More rain means more chemical weathering of the continents, which in turn draws more carbon dioxide out of the atmosphere. With this greenhouse gas diminished, the planet gradually cools down. Conversely, if the world enters an ice age and temperatures plummet, the rate of weathering slows dramatically. Ice sheets cover the rocks and liquid water becomes scarce, but volcanoes continue to pump carbon dioxide into the air. With the weathering sink turned off, the gas accumulates, the greenhouse effect strengthens, and the planet slowly warms back up. This exquisitely balanced system is powered entirely by the heat from Earth's core. Without that internal fire to drive the tectonic plates, the conveyor belt that recycles carbon would stop. The climate would swing violently between extremes, making the long-term stability required for complex life impossible. The very land we stand on and the gentle climate that nurtures it are both gifts from the engine at the center of our world. These ancient landscapes are the core's personal diary, written in stone. Places like the Canadian Shield or the vast outcrops of Western Australia are not merely old, they are archives from a time when the world was a fundamentally different place. The rocks here are the original pages of Earth's story, some dating back over 4 billion years. They tell of a planet with a much hotter interior, where the core's engine ran with a ferocious intensity we can scarcely comprehend today. The heat flow was immense, driving a version of plate tectonics that was likely faster and more violent. In this chaotic environment, the very first granites were being extracted from the mantle, the foundational material of all continents to come. These cratons are littered with evidence of this fiery birth, from the remains of colossal volcanic outpourings to the twisted and folded remnants of the planet's first mountain belts, all forged in the core's initial, desperate efforts to build something permanent from the magma ocean's chaos. The true secret to their longevity lies not just in their buoyant granite tops, but in their hidden foundations. These cratons have deep roots, extending hundreds of kilometers down into the mantle. These are not warm, flowing roots, but rather cold, strong, and dense keels that act like anchors. They are the geological equivalent of a ship's deep, weighted keel, providing a stability that has allowed these landmasses to survive unscathed for eons. While the convective currents of the mantle have torn apart and recycled countless younger rocks, these ancient keels have insulated the Cratons from the destruction below. They have floated unassailable on the restless mantle, preserving the core's first and most resilient masterpieces. To walk on this bedrock is to touch the very first successful experiments in continent building, a direct connection to the moment our planet learned how to create lasting land. Granite is the signature of the continents, their fundamental substance. This light-colored, speckled rock is not formed from the simple cooling of lava at the surface. Its creation is a deep, slow cookery, a direct result of the heat and pressure engineered by the planet's core. The process begins with pre-existing rock, often the dense basalt of the ocean floor or accumulated sediments that is dragged down to profound depth. There, buried under dozens of kilometers of overlying rock and subjected to temperatures high enough to make stone soft, it undergoes a transformation called anaxis. This is not a full melting into a uniform liquid. Instead, the rock begins to sweat. The specific minerals with the lowest melting points, those rich in silica, potassium, and sodium, turn to liquid first, while the tougher, denser minerals remain solid. This selective melting is the key. It acts as a geological filter, separating the light, buoyant elements from the heavy ones. This newly formed magma, now a granitic soup, is significantly less dense than the solid rock around it. It begins to behave like a hot air bubble in a vat of thick syrup, sluggishly but insistently rising through fractures and weaknesses in the overlying crust. Its journey upward can take thousands of years. If it reaches the surface, it might fuel a violent volcanic eruption, but more often this magma gets trapped. It stalls in vast subterranean chambers where it is insulated by miles of rock above. Here, it cools down with excruciating slowness over tens or even hundreds of thousands of years. This gradual cooling is what allows large, interlocking crystals of quartz, feldspar, and mica to grow, giving granite its characteristic coarse-grained, speckled appearance. These hidden formations, called batholiths, are the true skeletons of continents. They form the deep, unshakable cores of mountain ranges like the Sierra Nevada, which are merely the exposed tips of these colossal granite giants after the softer overlying rock has been eroded away. Every granite peak, every polished countertop, is a piece of this refined, buoyant material that refused to be swallowed back into the mantle. It is the ultimate physical proof of the core's power to sort, refine, and build something permanent from the chaotic ingredients of the young Earth. The slow-motion collision of continents is one of the most powerful forces on the planet. This is orogeny, the ultimate act of mountain building, and it is the core's most dramatic display of strength on the surface. There are three primary ways this geological drama unfolds, each a direct consequence of the heat-driven plate movements orchestrated from below. The most colossal is the continental collision, a head-on crash between two unstoppable landmasses. Picture the ongoing impact of India into Asia. Neither continent is dense enough to subduct, so there is nowhere for the rock to go but up. The leading edges of both plates crumple, folding and faulting in a titanic upheaval that thrusts rock skyward to form the Himalayas, the highest mountains on Earth. A different kind of orogeny occurs at the ocean's edge. In an Andean-type event, a dense oceanic plate slides beneath a continental plate. The subducting slab not only fuels a line of volcanoes with its melting, but it also compresses the entire leading edge of the continent, squeezing it like a giant vise. This dual action of magma intrusion and tectonic squeezing uplifts entire mountain ranges, building the long, rugged spine of the Andes. But even the tearing apart of a continent can raise mountains. When a supercontinent begins to rift, the stretched crust fractures along great faults. Huge blocks of rock can tilt upward, creating fault block mountains with dramatic, sheer escarpments. The Sierra Nevada in California began its life in this way, as a massive block of granite heaved upward during the stretching of the western North American continent. Every one of these processes, whether driven by collision, subduction, or rifting, is fueled by the same source, the relentless heat escaping from Earth's core. This energy drives the plates into each other or pulls them apart, and in the resulting violence, the very architecture of the continents is forged and reshaped. These mountains are more than just spectacular scenery. They are the planet's most enduring monuments, built by the deep engine that will not let the world lie still. The same planetary engine that built our world is still actively redesigning it today. We can read the faint outlines of the future in the slow, relentless drift of the continents, a trajectory set by the mantle's deep currents. The Atlantic Ocean, born from the rift that tore Pangaea apart, is still a youthful basin. Its mid-ocean ridge continues to pump out new seafloor, pushing the Americas further from Europe and Africa. For now, this ocean is widening, but the mighty Pacific tells a different story. It is a remnant of a far older ocean, Panthalassa, which once surrounded Pangaea. Today, it is almost entirely encircled by subduction zones, hungry trenches where its ancient floor is being consumed faster than it can be replaced. The Pacific is inexorably shrinking, closing in on itself. These opposing motions are already setting the stage for the next great act in Earth's history. Look at the map of our world not as a permanent fixture, but as a single frame in a film that is still playing. Africa is slowly being torn in two along the East African Rift, a colossal wound where a new ocean will one day form. Australia is marching steadily northward on a collision course with Southeast Asia. These are not abstract concepts, they are the live movements of the planet's crust, driven by the same heat that has always powered the machine. Project this motion forward 250 million years, a mere blink in geological time. The scattered continents are predicted to converge once more, assembling a new supercontinent that scientists call a major or Pangaea Proxima. In this future world, the Atlantic may have stopped expanding and begun to close, bringing the Americas crashing into a united Europe and Africa. Australia could be sutured onto Asia's underbelly, and Antarctica might finally be drawn up from the south to join the tropical assembly. This new supercontinent will not be a copy of the last. The dance of the plates is never perfectly repeated. Its final form will be dictated by the slow, relentless churn of the mantle and the gradual, inevitable cooling of the core itself. Our planet's internal heat engine is slowly, over billions of years, losing its fire. The radioactive fuel is being consumed and the primordial heat is fading. This means the convection currents in the mantle will eventually slow, and the tectonic forces that reshape the surface will weaken. The formation of a major might be one of the last great continental collisions in Earth's long history. The core's work is never truly finished, but its tempo is changing. It continues to engineer the surface in a slow-motion ballet that will completely redefine the world for whatever future forms of life inherit it, crafting new mountains, new oceans, and new climates from the raw materials of our own. This hidden geological machinery is also the ultimate source of our material wealth. The same processes that build continents act as a planetary-scale refinery, concentrating rare and valuable elements into the mineral deposits that power our civilization. Consider the gleaming copper in our wires or the gold in our electronics. Their journey began with the relentless heat rising from the core. Many of the world's most important metal deposits are found in geological formations known as porphyry copper deposits. These are the treasure troves formed above subduction zones, where an oceanic plate plunges into the mantle. The magma generated in this fiery environment is rich in metals and water. As it rises and cools deep within the crust, the water and other volatile elements can no longer remain dissolved. They separate from the solidifying magma, creating a superheated, mineral-rich fluid under immense pressure. This scalding brine then forces its way through a network of tiny fractures in the surrounding rock, a process that acts like a high-pressure filtration system. As the fluid cools and its chemistry changes, it can no longer hold its metallic cargo. The metals precipitate out, coating the walls of the fractures with a fine dusting of copper, molybdenum, gold, and silver. Over millions of years, this slow, persistent process can create a single deposit containing many millions of tons of metal ore. But the core's role as a chemical engineer began even earlier, during the planet's violent infancy. When the molten Earth differentiated, the heaviest elements like iron and nickel were drawn inexorably downward to form the core. This great sinking act was a form of cosmic sorting. It left the mantle and crust relatively enriched in all the other elements that were too light or chemically incompatible to follow the iron into the abyss. This includes the precious metals we prize so highly. Elements like gold and uranium should, by all rights, have sunk into the core with the iron. Their presence in the crust at all is a geological puzzle. The leading theory suggests they were delivered later, by a cataclysmic bombardment of asteroids after the core had already formed, a final seasoning of rare elements that were then mixed into the mantle and concentrated by the very tectonic processes the core drives. From the iron in our skyscrapers to the rare earth elements in our smartphones, the concentrated mineral wealth we depend on is not a random accident. It is the direct and deliberate result of the core's 4-billion-year project of thermal and chemical engineering, a legacy of elemental refinement written deep into the bones of every continent. Our own solar system holds up a stark mirror to Earth's vibrant geology. Mars presents a world frozen in time. Its core has largely cooled and solidified, shutting down the planetary dynamo that once generated a global magnetic field. Without that protective shield, the Martian atmosphere was stripped away by the solar wind, and without a churning mantle to drive plate tectonics, the planet's geological engine seized. The Martian surface is a museum of ancient impacts and vast, dormant volcanoes like Olympus Mons, a single colossal mountain built over a stationary hotspot. There is no continental drift, no subduction, no slow-motion recycling of the crust. The land is static, leaving the planet's ancient, cratered highlands exposed to the elements for billions of years, with no mechanism to refresh them or build new, complex landscapes. Venus, shrouded in its thick, toxic atmosphere, tells a more cryptic story. Radar maps reveal a surface of vast plains and towering highlands, but there is no clear evidence of the shifting plates and mid-ocean ridges that define Earth. The leading theory suggests Venus operates under a stagnant lid mode, where a single, unbroken plate of lithosphere caps the planet. Heat builds up catastrophically beneath this lid until the entire surface is cracked apart and repaved in a planet-wide volcanic apocalypse, after which the lid reforms and the cycle begins anew. This is geology through episodic catastrophe, not the steady, continuous construction and renovation we experience on Earth. The profound difference lies in a planetary Goldilocks zone of size and composition. Earth is large enough to have retained sufficient internal heat from its formation and radioactive decay to power a mantle convection system for billions of years. Yet it is not so large that this heat creates a permanent, molten hellscape. Our planet found a perfect equilibrium with just enough energy to keep the plates moving and the core churning, but not so much as to prevent the formation of a solid, habitable crust. This delicate balance between fire and stability appears to be extraordinarily rare. The active core and the plate tectonic system it drives seem to be a special recipe, one that has so far yielded only a single world in our solar system with diverse, evolving continents and the enduring, gentle climate that life required to flourish. Yet the mantle's hidden structure holds even deeper secrets. For a long time, we pictured the mantle as a giant, churning blender, slowly homogenizing everything within it. But new evidence tells a different story. The mantle is not uniform. It contains distinct, isolated reservoirs of ancient material, vast chemical domains that have remained separate for billions of years. The clues to this hidden geography come from the unique chemical fingerprints found in certain volcanic rocks. The lava that erupts from hotspots like Hawaii carries a specific isotopic signature, a kind of atomic barcode that points to a source of incredibly old, pristine material. This is not the well-mixed rock of the upper mantle. This is primordial stuff, a relic from the planet's formation that has been sequestered near the core-mantle boundary, surviving the entire turbulent history of our world without being stirred back into the mix. Other deep reservoirs tell a different but equally ancient tale. They appear to be the sunken graveyards of oceanic plates. Imagine every subducted slab of ocean floor over 4 billion years, not completely melting and disappearing, but instead piling up on the floor of the mantle. These colossal accumulations of recycled crust are like layered history books, their pages written in basalt and sediment, slowly heating up and occasionally contributing their own distinct chemistry to the mantle's churn. These deep chemical domains act like different fuel types in the core's planetary engine. When a plume of hot rock rises from the deep mantle, it does not just carry generic heat. It carries a specific chemical cargo, a unique blend of elements from these ancient reservoirs. This cargo directly influences the composition of the magma that eventually reaches the surface. A plume tapping into a primordial reservoir might produce the unique lavas of Hawaii, while a plume melting through a graveyard of subducted plates might generate a different kind of volcano altogether. This adds a profound layer of complexity to the continent building process. The very nature of the new land being forged is not just a product of simple melting, but is subtly flavored by the specific deep reservoir that supplied the heat. The interaction between the convecting mantle and these stable, deep-seated domains is one of the most exciting frontiers in geology. It hints that the core's influence on our world is not just a blunt physical force, but a nuanced chemical conversation, one that has been quietly shaping the very substance of our continent since the beginning. Our planet hums with a hidden music, a vibration that travels through its very bones. We cannot see the engine room, but we can listen to its echoes. The science of seismology translates the deep groans of the Earth into a detailed map of its interior. When a massive earthquake shakes the globe, it sends out powerful shock waves in all directions, traveling through every layer of the planet. These seismic waves are our only messengers from the abyss. Their journey is not a simple one. The speed and direction of these waves change dramatically depending on the material they pass through. They bend, they slow down, they speed up, and some even stop completely when they hit a liquid barrier. By placing thousands of sensitive listening devices, called seismometers, across the world's surface, scientists can record the precise arrival times and behaviors of these waves from a single quake. It is a planetary-scale echolocation experiment. The differences in these recordings are the crucial clues. A wave that arrives slightly faster than expected tells us it passed through cold, dense rock. A wave that suddenly disappears reveals it encountered a liquid layer like the outer core. Waves that reflect sharply back toward the surface have bounced off a major boundary, such as the one separating the mantle from the core. By compiling millions of these readings from earthquakes across the globe, a process known as seismic tomography creates a stunning three-dimensional image of Earth's interior, much like a doctor uses a CT scan to see inside a human body. This is how we discovered the solid inner core, a crystalline ball of iron spinning within a sea of molten metal. This is how we trace the fate of a subducting plate as it plunges thousands of kilometers into the mantle. We can even see the ghostly outlines of superheated mantle plumes rising from the core-mantle boundary, the very blowtorches that build volcanic island chains. These are not artists' impressions. They are data-driven visualizations of the planet's living anatomy. The great conveyor belts of mantle convection, once just a theoretical necessity, are now visible in these subterranean scans as vast, slow rivers of rock. Seismology provides the definitive proof that the heat and churning motion born in the core are the direct architects of every volcano, every mountain range, and every new piece of continental crust. It is the ultimate validation that we live atop a world of fire, its pulse recorded in the shudders that pass through the ground beneath our feet. But this grand geological machine is not isolated from the world it creates. The continents forged by the core's immense power became the very cradle for life, and in a remarkable twist, that life began to talk back to the engine that built it. This is a symbiotic relationship, a deep and ancient dialogue between the living world and the planetary core. The stable, buoyant platforms of the continents provided the permanent real estate that complex life needed to gain a foothold. The relentless geological processes of mountain building and erosion, driven by the core's heat, broke down the primordial rock, releasing a wealth of essential nutrients and creating the deep, fertile soils that would eventually support vast forests and grasslands. The stage was set by geology, but life quickly became a lead actor, altering the very scenery it stood upon. The most dramatic example began over 2 billion years ago with the evolution of the first photosynthetic microbes. These tiny organisms began to pump a new, reactive gas into the atmosphere, oxygen. This was a planetary revolution. The oxygen reacted aggressively with the minerals in surface rocks, dramatically accelerating the rate of chemical weathering. This biological acceleration changed the very recipe of the continents, as the sediments washing into the oceans now had a different chemical signature, leading to the formation of entirely new types of sedimentary rock, like banded iron formations, that would never have existed without life's intervention. Life also became a crucial partner in regulating the planet's climate through the carbon cycle. When plants and microscopic plankton die, their organic remains, rich in carbon, can be buried in mud and sand on continental shelves or in deep ocean basins. Over millions of years, these sediments, packed with this buried life, are compressed into rock, locking the carbon away. When these sedimentary layers are swept into a subduction zone, they are cooked, and their carbon is eventually released back into the atmosphere through volcanoes, completing the cycle. But a portion of this organic carbon escapes recycling, becoming permanently stored within the continental crust itself as coal, oil, or shale. This long-term burial acts as a brake on the greenhouse effect, helping to maintain the stable climate that complex life requires. The core provided the heat and the motion to build the continents, and life, in return, learned how to help manage the planetary thermostat. We do not live on a planet with separate geological and biological systems. We inhabit a single, deeply integrated entity, where the fire below and the life above are locked in a billion-year dance of mutual creation. Our journey from the planet's iron heart to its highest peaks reveals a world of profound connection. The solid ground beneath us is not a passive stage but an active, dynamic creation, continuously shaped and reshaped by immense energies from the deep interior. That relentless heat from the core drives the mantle's great churn, which in turn moves the tectonic plates, builds mountains, forges new continental crust, and recycles the old in an endless, life-giving cycle. This is not a story of random chance but of planetary engineering on the grandest scale, a process that has meticulously crafted a world uniquely suited for life. To see the continents as engineered from below is to gain a deeper appreciation for our planet's beautiful complexity and its surprising fragility. This knowledge is more than just academic. It empowers us to understand Earth's deep past and to thoughtfully consider its long-term future, a future still being written by the fire within. If this deep time perspective has reshaped how you see the ground beneath your feet, we would love to hear your thoughts in the comments. And for more journeys into the wonders of our world, be sure to subscribe.